I'm Guangyuan from Renmin University in Beijing. Today, I'm very glad to share my recent research. Uh, the topic is double boosting of mean and dispersion in Tweedie's compound Poisson model for insurance loss prediction. So I will include those 4 parts: motivation, my proposed method, a simulated example, and the conclusion. So we started from a very common situation. Actually, we have some loss. We have claim numbers and we have claim size. So a standard method is Poisson for the claim numbers and gamma GLM for the claim size. Okay, so that is typically done in the most general insurance loss prediction. So it turns out if we only have the claim size denoted by yi, the marginal distribution is a Tweedie model, is a Tweedie distribution. It is an exponential dispersion family. And in this case, we actually we got a Poisson distribution. We have a gamma distribution, and if you do some integration with respect to the number of claims, we get the marginal distribution of claim size, and it turns out they have some relationship between the Tweedie parameter mu, which is mean, phi, which is dispersion, and p, which is the power index parameter. And the lambda is the Poisson mean. Alpha is the shape parameter in the gamma, and the tau is the mean parameter in the gamma. It turns out they have such relationship. I think those are derived in some textbook, and it turns out the dispersion is not constant. So here is my considered case. So in this research work, we focused on the scenario only the total claims SI are available. We don't know the number of claims. We have the total claims amount. And there are 2 existing methods. Both 2 methods are quite commonly used. If we can fit a single Tweedie GLM, and we just assume the dispersion is constant, because that is a single Tweedie GLM, or we can do a double GLM, which means we also fit, which means we also do a regression for the dispersion. However, both methods have some drawbacks. So the first method, a single Tweedie GLM, assuming dispersion is constant, it's not well, theoretically it's not a constant. Okay, so from the previous slides we know different policies just have different dispersion, and it's related to the frequency and the severity. And for the double GLM, it turns out when you perform the double GLM, you use the set point approximation, and it turns out when the proportion of 0 claim is large, this approximation is not accurate. So that is our motivation. So when you have when you only have the total claims amount, you cannot use Poisson for number of claim, gamma for claim size. You just do not have the number of claims, and the existing methods is just not good enough. Okay, they both have some drawbacks, especially for the double GLM. When we use the individual policy data, you will say nearly 90% of policies do not make any claims. So the proportion of 0 claims is very high. And in that case, double GLM just doesn't work. We will show this in the simulated example. So what is our solution? Our solution is we just treat n as some unobserved latent data. So rather than using exponential dispersion family, Tweedie distribution, we do not use that one. We stay with the joint distribution of n, but treat n as some unobserved latent data. And the typical way to solve this problem is well known, EM algorithm, expectation maximization algorithm. So it's quite intuitive to think of this problem, to think of this method. However, probably most people think it's too complicated to use the EM algorithm. In this case, we just use a simple model such as Tweedie regression or double GM. But it turns out it's not so difficult once you look at the expectation step and the maximization step. So I just want to skip all the technical details and we go, if I move to the expectation step, it turns out the joint likelihood can be decomposed into two parts. The first part is the Poisson part, the second part is the gamma part. So it turns out we can simulate several data points. Okay, so this is a key point. So actually, in order to find the MLE of beta gamma alpha, so beta is in the Poisson regression, gamma is in the gamma regression, we actually need to fit in two separate weighted regression models. So actually, we just go back to the normal case Poisson gamma model, but in this case, we generate several synthetic policies. Okay, so we know some policies made a claim, some policies without a claim, but for those policies with claims, we just generate the number of claims. We generate m synthetic policies for each policy with claims. So for example, if the first policy made a claim, if the first policy have some claim, we know the total claims amount. We can generate the number of claims. So can generate n equal to 1 up to n probably equal to 5. So for each policy with claims, we just kind of generate several synthetic policies, and we got augmented data. So this augmented data is larger than the previous data because we kind of expand the policies with claims. So in this case, we still do so that is what we learned from the expectation step, and in the maximization step we just fit two GLM, Poisson GLM and gamma GLM, but use some kind of simulated number of claims. And in those two GLM, it turns out we need to specify some weights because those from those expression we know the weights is different. So in general, the weights, so the sum of the weights for one policy is equal to 1. Okay, so that is what we got from the EM algorithm. So it turns out the EM algorithm lead to iteratively reweighted Poisson gamma regression. Okay, so each step actually corresponding to reweighted. We calculate that conditional distribution, which is the weight for every augmented data point, and the M step is just corresponding to the normal procedure, Poisson gamma regression. We fit two regressions separately, but we need to adjust the weights. So it's a kind of iterative process because the EM algorithm is just an iterative process. So actually, it's quite easy to implement this method, although it looks a little bit complicated EM algorithm. However, after some analysis, we can implement this method easily So we can first we initialize some parameter, and then we do a data augmentation. We keep the policy without claims, but we for each policy with claims, we just generate m synthetic policies. Those policies will with claim number equal to 1, claim number equal to 2, up to 5. Okay, so we generate this data, and then we will do a iterative process, include weights update and regression. Okay, for each of the for each number of claim, we have this weight, which is just the conditional distribution of n, and for the weight of claim amount, the weight turns out to be a number of claims times this conditional distribution. So this EM algorithm is equivalent to this iteratively repeated Poisson gamma regression, and we don't need to do anything else. So we are familiar with the Poisson gamma regression. So here I think it's easy, it's quite straightforward to implement this method, and we just overcome the drawbacks of the two existing methods. Okay, so for the single Tweedie GLM, we just assume phi is constant. Here, I do not assume phi is constant. Phi is the dispersion is dependent on the coefficient. And also in this algorithm, we don't need to calculate the power index parameter. If you go back to the Tweedie model, we need to estimate this power index parameter, and it turns out it's not so easy. You need to calculate the profile, log likelihood, and it's just a separate step to determine this p. But in our proposed method, we just generate augmented data and apply our familiar method to this augmented data, and we get everything. Okay, so there is an adds-on on this algorithm, EM algorithm. We can make a little bit improvement So I just replace the maximization by a boosting step, because boosting can discover some nonlinear effect and interaction effects. But I don't want to go in this deeper, because it's quite similar to the EM algorithm, just the EB algorithm. In the maximization, you probably do a Poisson boosting and a gamma boosting, that's all. So what is the performance of our proposed method? I use a simulated example. So this simulated example, I just assume 5 coefficients, 5 risk factors, and their relationship between claim frequency and claim severity is given by this eta and zeta. Okay, so lambda is the claim frequency, and the tau is the claim severity. So it's related to those 5 coefficients. Those 5 covariates. And we can see the 2 cases, large exposure and small exposure. So large exposure corresponding to, you probably observe this policy for nearly 5 years. Case 2, you observe for a short period. You probably just observe those policies for 1 year. And well, the reason we choose those 2 scenarios is because double GLM works when the exposure is large, because when the exposure is large, the proportion of 0 claims is a little bit lower. So let's look at the result. Okay, so this is a histogram of true parameter of true claim frequency severity, and the mu is the mean in the Tweedie distribution, and the phi is the dispersion in the Tweedie distribution. So the average claim frequency is around 70%, average size around 3,000, and the average pure premium is around 500. So for the large exposure, it says the proportion of zero claims is 42%. So that means more than half of policies make a claim because the observation period is long. We assume observe nearly 5 years. So during those 5 years, most policies make a claim. And we look at the performance of, so EB is the EB algorithm we proposed. The EM is expectation, so EB and EM are the two methods we proposed, and we compare with the two existing methods, a single Tweedie and the double GLM. And so those four models are fitted to the claims amount without knowing number of claims. And for comparison, since it is simulated data, we also fit two models. So two GLM to number of claims and the number of claims and the claims amount. Okay, so definitely those two models take some advantages because they observe more data. They observe the number of claims. And when we compare those models, we compare the test loss. We also calculate the correlation with the true mean, correlation with the true dispersion, and we find the EB just performs the best. EM is the second best, okay, among those four models. And surprisingly, EB and EM is quite close to this model, and this model assume N is observed. Okay, so it's almost recovers the information of number of claims. That is what we learn from the large exposure, and you say actually the double GLM works well if you look at the dispersion estimation. It should be fine. It's close to the result of EB. Okay, that is the large exposure. But if you look at the correlation with true mean, you see there is an improvement of the our proposed method. Okay, so especially for this one, for the EB algorithm, so it's 10% higher than the Tweedie GLM or double GLM. Okay, the gap between our proposed method and the existing method is larger when we consider small exposure, and you will say there is a huge improvement for the mean estimation. Here we got 0.46 correlation. However, for the Tweedie GLM and double GLM, it's around 0.37. Okay, and also for the dispersion estimation, you say for the EB or EM, we get these numbers, but for the double GLM, we just get the wrong direction. Okay, so let's summarize what we find during this research. So we actually propose a better way to fit marginal Tweedie compound Poisson model. When number of claims is not observed, we only have the number of size. We only have claim amount. We propose a better method, and it turns out some advantages of boosting. So boosting can discover some nonlinear effect and some interaction. So in most cases, especially in this simulated example, because the underlying method contains some nonlinear effect and the interaction, so EM algorithm is a little bit better than the EM algorithm. So I think that's all I want to present, and thank you for your attention, and I'm glad to take any questions.
thank you. So there's no questions that have come through as yet. So just a reminder, if anyone's got anything they would like to ask. Maybe I could ask you a question just while we're waiting. What do you sort of see as the next building on your work and this presentation, Guangyuan? What do you sort of see as the next step in what you've been working on?
Definitely, I will analyze empirical data set. Yeah, there are many public available data set include number of claims and claims amount, so I can compare the methods.
I have got one question for you, Chris-Eric, which you talked a little bit about your approach, and you also talked about the other German working group. Would you like to give us a bit of a comparison between the two different approaches that were being adopted?
Right, okay, that's a good question. My German colleagues, they have done an excellent job for providing a paper that deals with the same problem, and it was really amazing that it was done independently from my work. And they use tons of daily external data from cell phones in order to measure what they call affectedness. And then they aggregated it to weekly values and also aggregated it to 50 regions within Germany. But it tends to be very granular in how they approach the problem. According to their presentation, it is a huge amount of work, and they also mentioned that the data volume could explode and you are highly dependent on the availability and quality of external data. Well, on the other hand, my approach is much simpler and faster. It depends only on company data that you control. From my point of view, this is a big advantage. But of course, one could argue that my choice of smoothing function is heuristic and arbitrary. My S consisted of three parameters, A, B, and C, and I just picked them by looking at several risk segments back and forth and trying different values out. And of course, another thing is you cannot apply my concept to modeling GLMs. So their approach is more general, and my approach just deals with the specific topic with predicting claim amounts. However, my concept is good and flexible enough for this specific task. And obviously, the biggest advantage of my concept for practitioners within insurance companies is a much better cost-benefit ratio. Okay.
Thank you. We don't have any other further questions, so we might wind it up, unless there's any sort of closing comments from the speakers.
Yeah,
No?
I personally think it's quite. I personally think it's quite a pity that we didn't have the third speaker join us, because I was really interested in the concept of takaful insurance in Kazakhstan, which is a totally different topic, which I'm not accustomed to at all. So I was very curious to learn something about that.
Yes, I'm sure she will be disappointed that, for whatever reason, she hasn't been able to make it. All right, well, we might close it there. Thank you, everybody, for joining in. Thank you very much, Guangyuan and Chris-Eric, for presenting your work. Fantastic opportunity through this Congress to get to see what other actuaries are working on across the world. So really appreciate it. Thank you, everyone.
Okay, thank you, Susan.